Alright, let's take a look at another quadratic reciprocal function. Alright, and if we actually take a look at this quadratic reciprocal function, if we look at the denominator here, this is a quadratic function, and we can actually, if we test this using the discriminant method, which is b squared minus 4ac, we can actually note that this is going to be a perfect squared trinomial. Now, one way we can tell that this is a perfect squared trinomial if the discriminant b squared minus 4ac is equal to 0. Right? So in order for me to test for this, I'm just going to write down my coefficient and my constant values. So a here is 1, b here is -8, and c here is 16. And I'm getting these values because I'm looking at the standard form of a quadratic, ax squared plus bx plus c. Okay, and you can notice here that if I plug this in, you get -8 squared minus 4 times 1 times 16, which is basically 64 minus 64, which is 0. Okay, so this is equal to 0. So because this is equal to 0, this implies that we have a perfect square trinomial. And if you have a perfect square trinomial where a is equal to 1, then you can actually factor it as x plus 1/2 b squared. Okay, so if b is equal to -8, 1/2 b is equal to -4. So technically, I can factor all of this into x minus 4 squared. So I'm going to rewrite this function as f of x is equal to -2 x minus 4 squared. It actually seems a lot less intimidating now, is the minus 1. Okay, so let's take a look at the domain and range of this function, right? So this is the function I'm going to be using now. Let's take a look at the domain and range of this function. So I'm going to start with the domain. So the domain here, x belongs to the set of all real numbers. We can understand that x cannot equal 4 because then you would basically have a restriction on the denominator, and that's not gonna, that value wouldn't exist, right? If we take a look at the range, we can say y belongs to the set of all real numbers, but y here cannot equal -1. And the reason y can't equal -1 is because this portion here cannot equal 0. And the reason this cannot equal 0 is because a fraction can only equal 0 when the numerator is 0. In this case, the numerator is -2. It can never be 0, so 0 minus 1 doesn't happen. So that's why y cannot equal -1. Now, after we find the domain and range, what we're going to do next is we're going to find the restrictions. The asymptotes. And the asymptotes, the vertical asymptote is the restriction on the domain, so the vertical asymptote is x is equal to 4. The horizontal asymptote is the restriction on the range, which is y is equal to -1, so we understand that. The next thing we want to do here is also find our intercepts. So if we want to find our intercepts, I'm going to find my x-intercept and y-intercept. Let me start with my x-intercept first. And to find my x-intercept, I'm going to let y or f of x equal 0. Well, if I let f of x equal 0, we get -2 x minus 4 squared minus 1 is equal to 0. I'm going to move the -1 to the other side. You get -2 x minus 4 squared is equal to 1. What I'm going to do is I'm going to do the reciprocal so I can solve, right, for x. So you get x minus 4 squared over -2 is equal to 1. I'm going to multiply this by -2. Whatever I do to one side, I'm going to do the other side in order to solve for x. So you get x minus 4 squared is equal to -2. I'm going to square root both sides to get rid of the square root. You can actually notice that there is an issue here. Okay, so you can actually notice that, if I square root the -2 here, this is undefined. So this implies that there is no x-intercept. Right? So there is no x-intercept. And basically what that's telling us is that this numerator here can always, the denominator here is only positive, right? So you can notice that this value will always be positive. So because this is always negative, right? Negative divided by positive is negative. Negative minus 1, this value will always be negative. So this tells us that f of x will always be less than or equal to 0. Okay, so this is basically the idea, right? Well, sorry, it's f of x is always going to be less than 0. It's always going to be negative. It can't be positive. So f of x will always be less than 0, right? So it's always going to be underneath the x-axis, right? So that as a result, there is no x-intercept. So this is very important to understand. We can attempt to also find our y-intercept. So if I'm finding my y-intercept, I'm going to let x equal 0, excuse me. So if I do f of 0 here, we get negative 2 over 0 minus 4 squared minus 1, which is negative 2 over 16 minus 1, right, which is basically negative 18 over 16. Okay, so negative 18 over 16 you can write as negative 1, 2 over 16, or 1 over 8. Okay, so that's our values. So our y-intercept does exist. We have 0 and negative 1 over 1 over 8. Okay, and what we want to do now is let's sketch our function out. Okay, so let's plot our vertical asymptote, our horizontal asymptote, and let's get an idea of what this graph will look like, and then we're going to take a look at end behavior. So we notice that, right, this graph should not cross the x-axis, and that y should always perpetually be less than 0. Okay, so let's take a look at, let's say we go by 2's here. Okay, so I'm just going to kind of create my Cartesian plane. Okay, so we also can understand here that our vertical asymptote is 4. So I'm just going to draw my vertical asymptote in red. So x is equal to 4. Let's say it's like here. This is my vertical asymptote. X is equal to 4. And my horizontal asymptote is y is equal to negative 1. Let's do that in blue. Right, so if it's negative 1, it's going to be somewhere here. Right, and you kind of want to use a ruler for this, right? I should be using a ruler, but you know, I'm just kind of showing you guys as quick as possible just the procedure so you guys can learn it. And in this case, we want to find the intercepts, right? Well, we want to plot the intercepts. There's only the y-intercept, so if I plot the intercept, we have negative 1 over 8. So it's a slightly slightly below. We have 0 and negative 9 over 8. Okay, and using this notion, we can just kind of create a sketch here, right? So we can notice here that the graph is going to follow the confines of the asymptotes as shown. Once again, it's a sketch, right? If you want a more fine sketch, you would basically use a series of points, right? And because the graph doesn't cross the x-intercept, we can understand that the other graph here should do the same thing. So it should kind of do that, right? And so the graph here will be below this horizontal asymptote. So let's take a look at our end behaviors. See the different color here. Let's take a look at our end behaviors. Right, so to assess our end behaviors, I'm going to say x approaches negative infinity. So as x approaches negative infinity, you can see that y gets closer and closer to the horizontal asymptote from below. Y approaches negative 1 from below. As x approaches, the next step here is let's approach the vertical asymptote 4 from the left side, and we'll also approach the vertical asymptote 4 from the right side. So as x approaches 4 from the left side, y actually gets closer and closer to, if you follow the trace, it gets closer and closer to negative infinity. Right, as x approaches 4 from the right side, as we go this way, right, y also gets closer and closer to negative infinity, because you can see that the trace gets elongated in the downward y direction. And as x approaches positive infinity, as we go this way, right, y actually gets closer and closer to negative 1 from below. Right, so there is a sense of symmetry, right, in terms of the approach to the horizontal asymptote and the approach around the vertical asymptote. So that's one of the hallmark features of these quadratic reciprocal functions, right? So it's really interesting to understand this, and this is basically, you can kind of glean a lot of these characteristics by sketching the function.